What we're going to do is we'll start with the soft project. So Pavan's going to speak about anomalous diffusion with fractional derivatives.
Thank you, Anaga, for introducing me. It's a really nice opportunity that we have a different community people present in one room. Generally, that's not the case. So hopefully, I can present it today in a more holistic manner and get your opinions as well. Please interrupt me wherever you feel like there is an opportunity for a good conversation. So I'll get on with my talk. I'll start with some basic introduction, and then I will in the second part I'll have my proposition for the for the turbulence model. Then I'll introduce tempered fractional calculus. Finally, I talk about some boundary layer, and if time permits and someone is interested, we can also talk about numerical algorithm is how to compute the fractional order. I have tried to be as concise as possible, and but if there is something that is missing and it requires further explanation, do interrupt me. But I've tried to be to fit in everything as much as I can in one presentation. So the governing equation for turbulent flows is no doubt the Navier-Stokes equation. But in order for me to actually so solve this equation, the time and spatial scales are very small, and for me to resolve it, it requires me to build grids that are increasingly fine, and it has been a computational challenge. To my knowledge, and if my memory serves me well, the biggest simulation was on homogeneous turbulence by either by a group led by P.K. Young in Georgia Tech, or probably by the German group. I'm not sure which of the two simulation is the bigger one, but the point here is that the computational challenges are big enough that it drops the biggest supercomputers. But given that someday we have a big enough computer, we might stop discussing a bit of turbulence modeling, because at the level of Navier-Stokes, I actually do not need any model at all. I can solve the Navier-Stokes, which is F is equal to ma equation, alongside with the conversation of mass, and then for an incompressible flow, I just have the Poisson's equation, and the system is complete for me to solve. But today is not that day, so modeling is very relevant, and especially to the engineers. To the engineers who look into very complicated flows to design machinery of use. So one primary motivation was like, all right, so if we cannot solve Navier-Stokes and we want to make it computationally cheaper, why not directly look into the mean fields? When I call mean fields, that implies that it is basically temporally averaged. So Osborne Reynolds took the Navier-Stokes equation, and then he time averaged the whole equation, and that led to equation number 2 on the slide, which bears his name, which is Reynolds average Navier-Stokes equation. So the every quantity u bar over there is actually a mean quantity, and from the nonlinear term we actually have an additional term, which is the little ui, little uj. Everything with little ui and little I would imply that it is a fluctuating quantity. So that has the units of proper units of stress as well. There is a viscosity term that's missing. Sorry, but and the whole community of turbulence modeling is actually trying to figure it out, what exactly that term behaves like, and since the time of Prandtl and von Neumann and Richardson, Brian Launder, and I can name a lot of them, they proposed quite many theories and mathematical models. How do you close this system? Because now the problem of closure is that you have lesser number of equations and more number of unknowns, and hence the field of turbulence modeling. In this case, I'm just going to be non-dimensionalizing with u tau and viscosity. The reason I'm actually non-dimensionalizing is because at some point I'm going to be introducing a fractional derivative, and then it would not be unique. It would not be consistent dimensionally speaking, because then the fractional derivative will give you a quantity that is dimensionally inconsistent. So you want to maintain the dimensionality of it. So non-dimensionalizing is the proper way of going through, and then the whole exercise is like, how do you match the numbers by your construction? So the high level idea is that you take the total shear stress, and that is the point you introduce the fractional derivative. In the next slide, I will talk about two such constructions. One thing I have to point out here is that the usual approach has been looking into modeling those little ui and little uj bar terms. That is what we call is the Reynolds stress. But my proposition is that don't look at the Reynolds stress. It actually model the whole stress term together with its local part that was because that I understood it was more of a consistency argument, which I will probably talk about in the next slide. And one thing also I have to add is that the fractional order is actually not a constant, but it is a variable order. At this point, we do not know what that order is like, but then we had numerical methods to actually determine it by using the databases that the people in the turbulence community have been generously kept open source, or in some cases they have personally sent it to me to facilitate the research. So I have two model constructions. One I'm going to call it as the one-sided model, and the other one I'm going to call it as the two-sided model. And we'll immediately learn what are the properties of all this, what the fractional order looks like. So when we take the test cases for the two-sided model, we have actually the left and the right Caputo derivatives. For the one-sided, we just have the left-hand side Caputo derivative. For either cases, the fractional order is variable order. For my initial test, I'm going to look into the canonical flows that have been sort of quite well established at this point, which will be the channel flow, the quad flow, and the pipe flow. So this setting is that there are two parallel plates for either of the cases, and for the channel, the two parallel plates are actually at rest, and for the quad flow, one of them is moving at a constant velocity. So for the case of the fluid, that is what is driving the flow. The ones that are not shown are actually computationally we keep it as periodic, so that becomes a computationally tangible simulation to do. And for the pipe, it's pretty much the similar as in the channel, but now you have the homogeneous direction, which is along the theta direction or the azimuthal direction. I want to actually talk about the picture on the top. That is an actual simulation by a group from Johns Hopkins University, and that's a simulation of the channel flow. If memory serves me well, the Reynolds number R eta was around 5,000-ish. Around 5,000-ish. So you can appreciate the number of scales that actually turbulence has, and it is a very chaotic phenomena, and hence it has been quite a challenge to actually develop turbulence models for this very same region. But if I have to take the time average, you won't see all those scales, and you just have a nicely behaved mean. But then you have to talk about the closure as well. So otherwise modeling, that's why the modeling is actually quite complicated. So I'll start with some of the results for the one-sided cases. Zero in all of those plots is actually the physical the physical wall, which is the lower, and for the one-sided model, I'm just going to the domain of computation is half of it. So if example, from wall to wall, it is the height is 2h, twice the h, and for the one-sided model, you only look at the center line. And if I have to convert into wall units, then at the center line it is RE tau, and wall to wall, it's the domain is 0 to RE tau. RE tau implying it's a friction Reynolds number. So immediately near the wall, what we have is that the fractional order is unity. That was actually by construction, because at the viscous sublayer near the wall, what we have is a scaling of velocity that is proportional to the to y plus, and that's true to y plus roughly around 1 pi. So we have a viscous sublayer, and the Reynolds stresses are completely absent. So it makes sense that thin region near the wall, that this thin region near the wall is viscous dominated is purely by the local operators. But as we go beyond the wall, non-locality enters, the turbulence intensity increases, and as a result of the turbulence action, the Reynolds stresses are non-zero, and non-locality being resided in the Reynolds stresses.
Can you go back to the previous slide there? Okay, so I'm sure that the people from one community are okay, but I need how are the fractional derivatives shown here? What's the notation? What does it mean? What is a left and right side of fractional derivative?
So that's actually a definition, but
Yes,
which I have not shown. So basically, it's an integral with the lower with 0 to y plus implies that 0 is the lower limit of that integral, and y plus is the other limit of that integral, and then we have a kernel, which is a power law times times du by dy.
And the power is the alpha? No.
Yes, exactly.
And it depends on y.
Yes, it's a spatially varying
So a different
order.
power for every
Yes,
every height.
exactly. So it's a different order at every. It's spatially different, spatially varying.
I need to deal with that?
Yeah.
All right.
And I'm going to make some interesting remarks actually. Sorry. Oh, C is basically a notation. C implies that it's a Caputo derivative. So there are different types of fractional derivative. We have a Riemann-Liouville definition as well. So in order to make distinguish what sort of definition we are using, those subscripts are actually very common in the literature. So the C implies it's Caputo.
And what does that mean?
It's a Caputo fractional derivative. So it's a definition of the derivative.
Yes, but what is the difference between the different kinds of fractional?
Oh, there is a difference of the definition.
Okay.
And for
So here you only apply the fractional derivative in y direction.
Maybe you can write the formula with them.
yeah, okay.
That's okay. Don't worry about it. It happens every time. It's all right.
Probably the next definition I'll write with bigger letters. So if you want to actually talk about it, where this actually is coming from, the good discussion I personally find is the definition of German written down, and in a moment I'll actually even write that as well. But this is something that you might find it in literature. So think of this. The basic definition, what exactly du by dy is. So what you can do is write the limit of h tending to 0, and then you will have f of x. Okay, f of x plus h. So this is what the definition of derivative would presumably imply, and then you want to write it for the nth order general definition. That nth order general definition is you can rewrite it in a form of a binomial coefficients, and that those binomial coefficients are generally you can further generalize those binomial coefficients by using the gamma function. So now that definition it can be now defined over the whole range of numbers rather than just the integer order numbers. So, but I'm not going to go much in detail about fractional calculus because where do I even because I want to talk about my results, and those itself are like 40 slides to be covered in 1 hour.
So relatedly, so what's the, I guess, 2 questions.
Yeah.
So you have the RAND model. I think a RAND model is there's a model for the Reynolds stress. Plug back into the
Okay, go on.
To the time average, Reynolds average, and average Stokes equation.
Yeah.
Correct. So what's
the model? That's the model actually. So so generally what you have is for the runs, right? What I'm telling you is when you look at the stresses, consider it with the viscous stresses, combine the two, that is equal to fractional. Go back to your Lagrange equation, plug it over there. And
so I solve that equation for the Reynolds shear stress and plug it into the RAND equation.
Yes. For right now, you will keep it to this level, and then you can. But ordinarily, you would not know that. So the system of equations you want to solve is no system of equation. But given that what fractional order it actually looks like, at the moment I'm in the journey of finding the fractional order. So I'm going to take the DNS databases and just find the fractional order. But when I'm solving it otherwise, I have some fractional orders. I can just solve the whole system of equations and not worry about this. Am I making sense?
Okay, well, I guess
So
my second, I guess that leads to my second question. So you're determining alpha from data through some fitting process.
Exactly. Yes, that's correct.
And back 1 or 2 slides. There. So maybe.
Yeah, I just introduced an M notation randomly.
Oh, okay. So just wanted to say to the colleagues from the other community that these equations are equations for U bar, which is what you need, but what you don't have is the UI UJ bar, the little ones. And so the whole problem is how are you going to approximate that UI UJ, a little UI UJ, so as to have an equation that's only in the bar quantities. That is the problem. That's the fluid problem for fluid mechanics. I just wanted to favor explain to those.
Thank you. Thank
So
you.
that's the problem, is that little UI bar term, which isn't VUI.
So you're taking a DNS, you're finding the 2 terms on the right-hand side, the derivative of B.
Yes.
And then you're finding the Reynolds stress.
Yes.
And then you're finding a value of alpha for that derivative that gives a good fit.
Exactly. And I have a numerical algorithm, which where we talk about physics informed neural networks and so on and so forth, whole other discussion. But which we can go in at the end of the lecture if time permits, or probably after how do you determine it. But at the moment, the answer is yes. Let's move on. Oh, it's on top. No, look,
Distance away from the wall.
it's look.
So the normal direction of perspective.
You look, yes.
So your reflection will be only the quantum perspective.
Yes, for this case, you can actually, the only variation is along the y direction for the mean. The rest terms actually die out.
What happens now X and Z?
No,
Those are only in those directions. There's no reason why there would be any difference between any. There's no special X values, there's no special Z values. They're all the same.
so okay, so all right. So then in the viscous sublayer, indeed the fractional order is 1, and as we move along to the outer turbulent region, we find that the fractional order is no longer an integer. It is less than 1, implying that there is non-locality present in that region. Interestingly enough, for the one-sided co-ed flow, if I just plot it over the y plus, it's entirely universal. But when you that was actually quite encouraging, and then we went around to do channel and pipe, and then we found that in fact that behavior was no longer present, and then we had an artifact. For example, the value 1 over there, the fractional order is actually unity. Numerically speaking, that is a solution, but physically that's just nonsense, because at the center line of the channel is just the turbulence intensity is amongst the highest anywhere in that region, and that's just actually quite nonsense. And in fact, and the reason of such problem is because the channel and the pipe have quite a symmetry, and then because of that symmetry, the construction that we have gives an arbitrary answer. So we went around, and then he was like, all right, the proper way to actually address the physics is to actually take both the sides contribution. Now, now why would you do that? If you're sitting at a point and you're trying to see what is the disturbance at that point, it's not influenced from the left, it's actually influenced from all the sides. And the amalgamation of everything is the disturbance I feel when I'm sitting at a point. So it makes perfect sense to actually use a two-sided model that takes the contribution from both the walls rather than just one of the walls. And that artifact that in the channel and the co-ed that we had is just disappeared, and we have now physically consistent result.
Can I ask another question here? So this kind of comes back to this point about one-sided not fitting well. So you got a value of 1.
That's the artifact of the symmetry.
There's some fitting process here, least squares or something, that should give you an estimate of the
numerical.
how good you're fitted.
No, numerical algorithm is all right, and we'll go about it. There's not an issue with numerical algorithm. What is an issue is that numerically speaking, for that one-sided model, that is actually a solution to it. So it's not the problem of the algorithm; it's the problem of the construction. So the construction is wrong.
Goodness of fit.
No, it's not something to do with the goodness of the fit. It's brilliant. It's all right. So because the reason I'm emphasizing on this, because it's the construction that is going wrong, not the algorithm.
No, I know, but my point is just that if the construction has gone wrong, the process of determining alpha should somehow give you a clue to that.
No, it's actually a solution. I went back and forth, and that is an actual solution. There is only one solution to it, and the fractional order that I've computed is an actual solution. So it's nothing to do with again. So I can do the reverse exercise. Now I have a fractional order. I can plug it into my definition, and then I see how well do I actually match the total shear stress. And if I actually compute the errors are less than 1%. So numerical algorithm is not going wrong. The part that is going wrong is the construction of my model.
I'm sorry, no, you said there are different constructions of alpha that can be constructed.
Yeah, there is a one-sided model and there is a two-sided model.
The computer data is usually used in time and as a memory kernel somehow, which makes sense in one side.
Yeah.
And
Yes.
here the problem is not in time.
Oh, yeah, no,
Yeah.
I understand.
Yeah, so it's a simple
There's
diffusion
no reason
process.
after really expect it once
But we can go back about the numerical algorithm, and when we reach there, and then that should answer some of your questions and any doubts you actually have. But thank you for asking that question because it's important for me to emphasize it.
Then reason alpha can always listen to one.
One of the
Go back to the previous slide. Is there any reason alpha always approaching one?
yes, because at both the sides of the wall, because of the presence of the wall, you have viscous sublayer in both the sides of the wall. So the examples under consideration are actually perfectly symmetric about the midplane.
There's no
No,
reason.
I'm not talking about symmetry. I don't know why it's
One.
approaching
Value,
one.
one.
Already one.
Oh, one.
Yeah.
Okay, that's okay. Okay,
There's no Reynolds stress.
exactly. There's no Reynolds stress. It's a viscous sublayer in both the sides.
That's on your equation, your definition, computed derivative equals mean velocity gradient minus Reynolds stress. Reynolds stress is 0, the computed derivative has to be the regular derivative.
Exactly. That makes sense, right? But I have an entire slide ready to talk more about it. But first, I want to establish some other things, and then we make comparisons. So I just wrote everything on the board. So sorry for that, but okay. So now I'm gonna what I'm gonna do is actually take all my data and plot it over y plus for the two-sided model. And interestingly enough, what I see is that in the viscous sublayer, there is a notion of universality. The buffer region also matches very well, and what we see is that around the wake region, this curve actually deviates from let's say if there was a given reference universal curve, and then at the wake region this curve deviates. And the reason I want to talk about this is that when we talk about velocity, we also have a similar discussion to be made, that is the law of the wake. So that we make for the velocity, it's a similar discussion. I can actually make it for the fractional order as well. And furthermore, if I have to suppress my wake and somehow try to find that universal curve, I can actually do that. It took me a lot of time and effort, honestly, but yes. Yes, so I have some nice universal curve when I subtract out my wake, and then I take my minimum alpha for pretty much all of my Reynolds number. Then if I simulate one of my alpha, one of the at a certain location, if I actually try to plot as a function of Reynolds number, what I see is that there is a nice power law for the higher numbers, not for the low Reynolds number. Well, for the quit and the channel, I do not have the velocity for high Reynolds number, so I fabricated that part of the data. But for the total shear stress, I had the perfect expression that I can derive it. But for the pipe, I had data from the Princeton super pipe experiment. So I was able to fit a nice looking power law. So that one property of the power law is that at some point it will asymptote. So empirically speaking, there exists a value of fractional order that is for arbitrarily high Reynolds number, and to further actually talk more about it with comparison to the velocity. For such cases, we have a nice logarithmic velocity profile in my head, this is analogous to actually a power law in fractional has a similar meaning of having a logarithmic region of velocity. So what happens is that in the near world region, we have a scaling that is u plus proportionally equal to y plus. That's the viscous sublayer. Then there is a log region and there is a weight region. I talked about the weight too. We can decompose it as we do it for the velocity. So for the logarithm for the so the log region, what I have is what I see is a similar behavior, but the fractional order is in fact a power law, and I have so all the arguments that I make for the velocity, I can also actually make for the fractional for the two-sided fractional model, like the decomposing the weight, log region, power law region, viscous sublayer being universal, but in this case the buffer layer is almost universal for different types of flow. I've unfortunately not plotted over it, and I realized that there is a point of departure where for the fluid and the channel the fractional order will depart, but it's in the vicinity of the buffer layer or a little bit higher than the buffer layer. So I have some scaling available for the buffer layer, which personally I'm not quite aware of having something for the velocity. That would be my limitation, perhaps. Well, it took me a while, but I was able to find some analytical expressions as well, and the building blocks were pretty much everything that we discussed, that having the power law and many other things. So it took me a while, but all right, I have analytical expression. This one? Oh, this one is pure fitting, empirical, but it took me a while to actually find it, but yeah, but it's purely empirical. There's no derivation for this. So it's just trying to fit all the fractional orders. Then I just try to derive, find an expression if I can. I happen to actually see a paper from the late Professor Mark Meerschaert, and he introduced tempered fractional calculus, and I thought that this might be a nice logical extension. So the idea is that what Mark proposed, that besides the usual power law kernel, one could also introduce an exponential term, which is the exponential tempering. And I was of the opinion perhaps this discussion can be extended to any tempering distribution, and to my personal use will be what one Mark did was use the exponential tempering. Then I would also like to use Heaviside function, so I can truncate my domain, the domain that then becomes a sharp cutoff. I will introduce that definitions in a bit, but I want to also talk about Dirac functions and its importance. There is a paper by Kreitman, much earlier than before we all of us started before I even started talk about non-local modeling. His model cannot go back to local, but I think if there is such a construction, I can introduce a Dirac function, and probably I can make the non-local model go local as well, because apparently there is a duality near the wall region. When the fractional order is unity, it makes perfect sense to actually have a local operator, and beyond that viscous sublayer, you need a non-local operator. So this duality is actually becomes very difficult to actually address it. I was lucky because fractional operator naturally by definition addressed all those things. So, yeah. So I'm gonna call the tempered distribution, tempered definition. That would imply that I will have a tempering distribution as an exponential. That's my construction. I have some other term as well. And then I will have a truncated definition as well. Well, where the domain is governed by the delta, that the delta I have. Okay. But by delta, and now there are two parameters unknown, which is the fractional order as well as delta for the truncated definition, and for the tempering there is lambda, and I want to see what happens and what more I could do with this. Obviously, the two-sided definition will have the similar structure that it has that we have been talking about. And okay, is there anything else I have to talk? Okay, no. So what I'm going to do is that I'm going to fix a particular lambda for the tempered definition, and I'm going to find my solutions for the fractional order, and I see that as a function of lambda, the fractional order, there is a solution. There is no such thing as the best solution, because I can take that lambda value, corresponding alpha value, compute my fractional order, and I will have within 1% or 1% error. So I don't believe that there is the notion of best solution. There is a space of solution, not just one solution. But the interesting thing to note as the exponential is a nice smoother value, you get a solution that is actually very smooth as well. Since there is okay, but in the case of truncated definition, it is a sharp cutoff, and that sharp cutoff will have a domain which you plotted as a function of y plus. You will see a point of non-differentiability as well, and all of these curves in here also have a point of non-differentiality as well, and it is exactly where the at the quoted delta values. The reason I find this as the notion of tempering as an interesting exercise, because if I have to solve this numerically, the fractional operator itself is an integral over the whole domain. If I had a truncated definition, and I'm not projecting on a spectral space, but I'm just solving on a real space, it is lesser computations for me, because that integral domain is that the domain of integral is not the not the whole domain, but some small domain. Of course, there is some equivalence between the two, and this is a plot of equivalence. So what I did was to compute these curves first, and once I have computed these curves, I have a fractional order. Then the logical question is that what is the corresponding delta value such that this will give me nice smooth solutions. And it so happened that delta is no longer a constant, but delta is now a function of space as well. So we saw in the previous plots, if delta is held constant, then you have point of non-differentiality in the fractional order. But if you want some smooth curves, then you can also have then you'll have to keep the delta as a spatially varying, and for both of the cases you'll have the same fractional order, and you can find the corresponding lambda or the delta. So numerically speaking, I can find an equivalence between the two, but I have to mention that I don't really have an analytical proof showing the equivalence. Yes, if I compute everything, and then the value of the total shear stress of the derivative itself is the total shear stress, and which matches very well. Some more plots of total shear stress. Yes, it matches very well. So all right. Now I want to talk about Now I want to talk about its application to boundary layers. So this was very encouraging results for us, and probably was one of the first extensive studies. So we said like what more we could do. So we started with turbulent boundary layers, but then we also looked into transition, and after that project was transition, we went around doing separation as well. We just kept challenging ourselves to find some either a nice property or a nice or a limitations, but we in a bit you will see that we do have fractional orders for all of these cases. But let me explain first by what is happening here. The picture on the right hand side, it's turbulent. On the left, on my far left over there is laminar. In between there is an emergence of the spots, of these turbulent spots, and as it propagates in space and time, not only the spots becomes bigger, but the two or three spots can come close to each other, and then the whole flow eventually becomes turbulent. So this is a bypass transition simulation done by the group led by Professor Tamizaki at Johns Hopkins, who helped me out with his data to play with. Again, so okay, so with the discussion of boundary layers, we also were looking for like what more can we build a wall model as well. So we started with the one-sided definition, but it has solutions that are interesting enough for us, because then you're just looking at from near to the wall to that point. You're discarding the other region. So it is computationally much more easier to do. And since we started with the turbulent boundary layer, we found that there is, within the literature, in the cited paper, there is an analytical expression for turbulent boundary layer for the expression of total shear stress. So we coupled together and then we computed all the fractional orders. So whenever you see the word ANA, that implies that the total shear stress is from this analytical expression. Whenever you see a DNS in brackets or something, that notation will imply that the total shear stress was computed from the databases. For either of the cases, the velocity was from the database. So we started the project on turbulent boundary layers, but then we also looked into transition. And now I'm going to talk about the results that jointly. So you have a fractional order as the flow becomes turbulent. The fractional order actually drops. So more the turbulent intensity, and lower the fractional order. But you have to actually make a remark in here that expression is only valid for the total for the turbulent cases, which is the far right. For all of the cases, that expression is completely wrong, but we can still find the fractional order. And if I have that fractional order corresponding to the right or the wrong expression, since the velocity was DNS, I can invert this whole system and compute the velocity. And I find that for either of the cases, I can match my DNS the DNS velocity fields. So that was quite encouraging as a wall model. So this one model can actually generate me velocity profiles for both transition as well as turbulent cases. For the sake of completeness, this is just plotting over y plus, and as you can appreciate is that as the Reynolds number increases, the fractional order actually quite decreases. At some point, it will also have the same discussions that we had it for the channel and the quote in the earlier discussions. For the sake of completeness, we also investigated for the two-sided model. The conclusions for the two-sided model are exactly the same as the one-sided model, but of course, the numerically speaking, the value of fractional order will have some differences between the two, but qualitatively, the discussions are quite the same. So one need to understand that the two-sided model will also take the region above the boundary layer. So, well, for the sake of completeness, we did actually look into it, but it's more convenient to just look from wall to that point, computationally speaking, because you can have different phenomena happening above it, and you don't want to ignore it. But okay. The next case, we were like, all right, since we have transition, we have turbulent, it makes perfect sense that, all right, let's look at separated flow as well and see and test our model, how well it performs. One motivation why we do such a case is that, for example, if you take an airfoil, which an airfoil is a geometry that is used to construct wings. So if you take a wing and you take a cross section, it will pretty much look like this. And you want the flow to be as attached as it is possible possible to your wing. So otherwise, what you have is that the lift and the drag would increase, and you will have a lift that will not support your weight of the aircraft and start falling off the sky. So you want to push this point of separation as downstream as possible. But if I increase the angle of attack, what happens is that the separation point will start moving towards the leading edge. Now, this is a qualitative example, qualitative motivation for doing such kind of flows, and but if I have to do it on non-curvilinear geometry, I want to keep it on want to keep my computational domain as the flat case. So what Van Wu and Charles Menu and the quoted authors did here is that you can take a nice flat domain in order to induce separation in the top boundary. At the top boundary, you can take that pressure gradient or that velocity profile and apply it to the top to the top of your computational domain, and that will induce a similar separation that you have it for the case of an airfoil. These notations I'm just using as the same as the quoted paper. So what the suction and blowing implies is that there is some suction that introduces adverse pressure gradient. So you have because as a result of suction, you have an adverse pressure gradient and your flow separates. But in order to make my mass flux as a constant, otherwise it becomes a little bit problematic to handle. What traditionally people do is also have blowing, so which is proportional to the suction. So the mass or relatively between in the computational domain remains a constant. So that's the suction and blowing case, but they also did when there was only suction only and no blowing. So the flow reattaches naturally, but in the case of suction and blowing, the flow actually reattaches as primarily as a result of blowing, and that blue region over there is a flow that is separated, and there is a recirculation bubble in that blue region. 4 minutes. Okay. So the intersection points are the reattachment and the separation region. So it's the same idea. The DNS or velocity within in the usual cases when we had a viscous sublayer, the fractional order was unity, but within the recirculation bubble, we do not actually have we have a stress term that is non-zero, and there exists non-locality at construction within that recirculation bubble gives corresponding results. But what was actually more what was more surprising is that when we use the wrong expression that is not at all valid for the total shear stress for the separation, we get really nice fractional orders that are quite smoothly behaved. And if I have to actually write an analytical expression, it becomes much easier for me to write an analytical expression for the analytical expression, and then just invert that system as a wall model. And it's the same conclusion for the suction for both the cases. One thing I have to point out, that when you have a wrong expression, of course it's wrong, so it doesn't even matter, but I have to point out that it starts giving signs of non-locality before the actual DNS does, which should be evident from the plot number A. So the similar is the case for both of the case. I guess I'm pretty much done. Do you want to talk numerical algorithms, or should I take questions? Okay.
How much better or worse does your model do compared to others?
Compared to others, as in what?
I don't know, because I don't know much about models.
Yeah.
Therefore, much better than K epsilon up. To actually tell you the truth, I'm not particularly aware there is a turbulence model for the case of a separation. So if you take this, and that is an open question, what is the analytical expression? But if you look at this and come up with an analytical expression, that will be the first model for the case of separation. And transition also is a problematic case, which personally I'm not aware if there is a turbulence model for transition as well. So the only bottleneck here is that how do you predict the point of separation? That has been my bottleneck.
Okay, so it's superior in predicting in treating separation.
And it's been consistent throughout. But any more questions? I want to add one more point, but okay.
Yes, so the two questions. So your introduction of the fractional derivatives in that closure equation, is it purely phenomenological, or do you have physical reasons?
There are physical reasons. Actually, that was the question I wanted to come back. So the hypothesis here is that turbulence is not the standard diffusion; it's actually an anamolous diffusion, and that is the physical reason. The reason why we do that. Actually, before even we long talked about the fractional derivative, there is something called as non-Pitkin equation, which exactly does the same thing. So instead of invoking the gradient as fractional, what you have is a constant in front of it, which is not a constant, and that has been long studied in the cases of turbulence modeling, but we don't call it as non-Pitkin equation except for Richardson. But I'm not sure if we use it at terminology. The terminology in the turbulence community used is eddy viscosity. So that eddy viscosity, if you go on and actually do a little bit algebra, you will find that it's of the same spirit of non-Pitkin equation, and that was proposition of Randall, the simple mixing length model, and then the whole field of turbulence modeling has been actually focused on what is that diffusivity constant. That was the part I wanted to talk about, but okay. Hence analogous diffusion in my title, but I didn't have the time to actually
go into the
I think I can guess the answer to this question, but the alpha profiles would have some universality between different geometries as well, right?
Yeah, but the discussion is the same as in the velocity. If you plot the velocity, exactly. If you plot for channel and quid, you will find there is some some universal region, and there is a point of departure. So that's that's the same for the fractional order. So yeah.
One more question. So you're saying there are ways to bring up these alpha without using data. Is that what you said? Like, is there,
Sorry.
so to construct these profiles of alpha, this is, I'm guessing, data intensive. You need to give it the answer of function of y, right? So you're saying that there are less data intensive ways to create these alpha profiles.
I'm not also talking about how data intensive it is.
No, I meant in the last bit that you couldn't speak about today.
Which one?
The last bit, like the modeling of the alpha profiles, right?
Oh no, it's no. This appendix.
I guess my question is there a way to bring these alpha profiles without a priori knowing the velocity profile?
Okay, so now that's a chicken and egg problem. For example, think. No, it's actually a chicken and egg problem. So, okay, let's drop fractional, and let's just go to the traditional. So now you have an eddy diffusivity. You don't know what is your eddy diffusivity value. So you go on with your data, you compute it, and you find a nice fitting to that, and then you come back to your actual simulation. So now you know what is the eddy diffusivity value. So now you can simulate the flow that is under question. Do you?
No, I guess probably the answer is there on one side. There are analytical expressions that actually.
Oh yes.
lead on to-
Oh yes. So but first I had to go through the exercise of finding it with the data, and then I derived it and as a fitting to the as a fitting to the fraction. So I took it. So I took this where I computed from the data. Once I had this nice scaling and something, what I could do is do a numerical fitting exercise. So as a part of my numerical fitting exercise, I'm able to write an analytical expression. So these are, and the reason I'm talking in this manner is because I want to emphasize that these analytical expressions are actually empirical nature. So once I have this, I just plug in the value. I don't, and the system of equations is now complete. I can plug in my fractional order, and then I can compute my velocity fields from these equations itself.
So when you're fitting data, do you treat the low with the right constants?
Sorry?
With the fitting that you have for channel flow, for instance, do you retrieve the log layer with the right constants?
This is the match with DNS.
Yes. And it's using
Do you see? This is the match with the DNS. So it not only log low I'm talking about matching all the regions.
So, but then doesn't some laws like the log law will give you some constraints on the constants you have to put in it?
No, but I'm not using those constraints in this. So that's a separate research at all. So what I'm trying to tell you here is that whatever discussions you make for the velocity, you can make it for the case of fractional order, but you don't have a logarithmic region for a fractional order. What you have is a power law region which falls similarly within the log law region for the velocity.
So power law
In the velocity, no, power law in the in the fractional order, yeah.
We mean log for you.
Yeah, so that is an empirical observation. And if you're telling me if I've done it analytically, the answer is no, but that's an empirical observation.
Yeah.